Now let's turn our attention to mat foundations. Up to now in soil mechanics we talked about the settlement and the soil stresses induced by different shapes of foundations on a semi-infinite elastic medium using perfectly flexible foundations with a little bit by rigid. And those are very useful relationships, and we use them quite a bit. And I think it'll become clear as we go through this why that's the case. But now we're going to turn to different combinations of flexibility, and also in terms of the semi-infinite part. In other words, instead of just semi-infinite flexible or semi-infinite rigid, we're going to consider a finite soil mass, which ends in a what we call in soil mechanics foundations a competent layer, which are very, very common. At which point, all of the elastic settlement and stresses come to a stop, and we have a rigid stratum. And so, we're also going to consider another possibility. In fact, this is sort of a catch-all section where we look at different aspects of foundations, of shallow foundations, and we're going to talk about mat foundations, as you see here. With mat foundations, up to now we've talked about spread footings. And spread footings are spread, but they're not spread that much. Normally speaking, you have an array of spread footings, and you have an array of columns in the structure that transfer the load from the structure down through the footings into the soil. And the rest of if there is a floor, in some cases, like in bridges, the spread footings are pretty much the foundation. But in many other cases, you've got a floor between the columns, and the floor just usually kind of sits there. In the case of a mat foundation, that floor becomes an integral part of the foundation, and the entire plan form of the building becomes part of the support of it. And that usually, it would make sense that when you get that large of a spread of concrete and soil facing each other, that the flexibility of the mat will come into play. For serious analysis of a mat, if you feel you've got a serious differential or total settlement issue, you probably will want to engage some type of finite element analysis, especially in stratigraphies non-uniform stratigraphies, and to varying degrees, all stratigraphies are non-uniform. It's just a matter of how significant that is. So we're going to talk about that, and we're going to talk about what the effect of relative flexibility of soil and foundation, not just perfectly rigid or perfectly flexible foundations, have. But the first thing I want to talk about are floating foundations. Now, floating foundations are, those of you who had me in fluid mechanics laboratory, and for those of you who didn't, who are just watching this video, I have materials on this channel that talk about that particular topic. We have buoyancy, where we put a rectangularly shaped boat in the water. And when we did that, it sank to a level, and we compared the displacement of the boat to the weight which we had derived previously by weighing the boat. And ideally, the weight of the water which is displaced will equal to the the weight of the water that we displace will equal to the weight of the boat. And if you've got a rectangular type of plan form and straight sides, then you'll get a situation like we have here, where the volume of that displacement is equal to the length times the width times the depth, and then we can actually and if you have a uniform load on that, then we can essentially divide out the two lengths and the depth, and we can use a per unit. We can use a per unit area type of approach to determine how deep our ship will go. And we can do this something similar with buildings, although there's a little difference in that. The difference between a fluid and a solid from a stress standpoint is very simple. A fluid cannot withstand shear if it is not moving. Obviously, if it's moving, then the viscosity determines the amount of shear in the fluid. But if the fluid is stationary, then there is no shear. In a solid, there obviously is shear, and that shear is very important, up to and including maximum shear stress theory, which we also discussed in soil mechanics. In the case of soils, however, soils are intermediates. In fact, Verroit points out that we can consider very, very soft clays almost like a fluid, and we can also assume that their Poisson's ratio is a half, which is basically what a fluid has for Poisson's ratio. And so we can, but really it becomes, it's kind of a gray area. Most floating foundations are done on relatively soft soils, where the soil is approaching but not necessarily hits the fluid. And so with that in mind, we need to consider could we actually, like we did with the boat and the water, could we put a building in a soft soil and have it float there? Well, the answer is, if we're very careful, yes, we can. And this is illustrated here and here. And these two illustrations, and if you can't read them, you can pull up the slide presentation. We can, a true floating foundation, like over here on the left, basically, as we say, the weight of the soil is equal to the weight of the building, just like it was with the boat. And if that's the case, then we can do a little math, and if we have a multi-story building, then each story can be assumed to have a floor load of some kind of force per unit area. If it's fairly uniform, if we're not dealing with an industrial structure where we've got concentrated stuff. But usually, many times, even if you do in an upper floor, by the time you get down to the foundation, it's more or less uniform. If it's not, then you need to watch for it. You get to an eccentric loading situation. But in any event, that's really not germane to what we're trying to do. If it's uniform, then the weight, we can divide both the load of the building and the area of the foundation by that area. I mean, we can divide them out, and we have a per unit. And so on the left-hand side, the D, which is the depth that the building sinks into the soil, times the, strictly speaking, he's got density there, that should be a gamma unit weight. Benck Brahms, typically of older European engineers, thinks in terms of that nasty little kilogram force unit system, and I have a piece on vulcanhammer.info that discusses that particular issue. And so with that in mind, times rho, or which is actually, he's got rho as 18 kilonewtons per cubic meter, and we all know, don't we, that that's a unit weight, that's not a density, is equal to the number of floors times the load per floor. Say it's, in this particular case, he's got 10 kPa or 10 kilonewtons per cubic meter per floor, and you multiply the number of floors. If you've got the same on each floor, then you get, voila, building. So what he does is he multiplies all that through, and he ends up, and he solves for D, which is equal to N, which is a 3-story building in this particular case, times the delta Q, which is 10, over his unit weight in kilonewtons per cubic meter, which is 18, and he gets a weight of 1.67 meters. So therefore, that is the require that if he was, this was strictly we're strictly treating the soil as a fluid, then we can pretty much ignore, we can pretty much 1.67 is the depth that we have to have if we consider it a fluid. That's conservative because, as I pointed out a few minutes ago, every soils are able to withstand shear, and as a result of that, they are able to the fact that they can withstand shear means that they that you could actually go a little bit less. And we're going to see that on the other side here. He's got another example. The loading per floor is 10 kPa per floor, like it was over here. And there are 8 floors, so therefore the load on the foundation is 80 kPa. On the other side, things get a little nasty over here, and the reason why is because, for one thing, he's decided he would like to try 4 meters of depth. Now, 1.67 meters is not a lot of depth for a building, really, of this magnitude. But if you're, for example, you see very frequently in large buildings, you see parking garages in the basement. And there's obviously some utilitarian reasons why you see those. But on the other hand, the other reason is that they make a very convenient floating foundation. 4 meters, 12, 13 feet, that's decent parking garage. And that enables the cars to drive down to it. And also, if you have a flood, if your water table rises, which soft soil areas are really good for doing, then at least you don't lose the building. The cars will have to be replaced, but the building doesn't suffer that. So there are many different advantages to that. So in any event, he's got 4. Now, he once again decides to use those, not only this time those nasty kilogram force units, he uses CGS. 1.9 grams per cubic centimeter. If you another fluid mechanics fact, water has 1 gram per cubic centimeter. So then 1.9 is specific gravity of 1.9. He multiplies it by 10. He does another one of these little, we all know how it's done tricks, when in fact those of us who have been schooled on the pure SI system look at it and say, we really don't know what he's doing. And he ends up with basically 1.9 times 10 is 19 kilonewtons per cubic meter, which if you're working the SI system up to now, the true SI system, then that makes sense. So what he does is he multiplies that by 4, he gets 76 kPa. But his load is 80, his load, the wool he actually has is 80, so he's got an extra 4 kPa. Is that acceptable? You need to do a settlement and possibly a bearing capacity, although with large foundations you don't see much bearing capacity. And usually settlement is that you have to run a settlement analysis to make sure that the soil can withstand, will not excessively creep as time goes on. But the bottom line is that the answer to that is if the soil will withstand it, if the shear capacity of the soil will withstand the extra 4 kPa, and that's not much, then you probably have a viable foundation. So when analyzing floating foundations, You could say, well, we're just going to do with a true floating foundation, or you can say, well, maybe we could, reduce the depth a little bit because of whatever of the sheer capacity of the soil. So both of those are possible. Now we turn to another topic, and like I said, this is kind of a catch-all thing in that we have, we're going to talk about limited elastic soil depth and flexible and rigid foundations. We looked at, I told you what we looked at in soil mechanics. We looked at, mostly elastic solutions and semi-infinite homogeneous electric, and most of the time we were dealing with purely flexible foundation. Now, obviously, no right off the bat, a bell should go off in your head saying, well, is there really such a thing as a truly flexible foundation? Well, the answer to that question is no, there is not. But we analyze it that way. And the other thing we have to, and not only that, soil masses are not semi-infinite. As I mentioned earlier, we have usually a competent layer to put a stop to a lot of the effects of the softer soils closer to the surface. So between the two of them, we're going to try to work both of them at the same time, and hopefully we can unpack things in such a way that it's not confusing to you. We're going to define a large gamma. We're talking about the effect of the rigidity of the foundation. We're going to define a term, and we're going to spell that out in numbers in just a minute. If a foundation is purely flexible, gamma is infinite. If a foundation is purely rigid, gamma is 0, and anything else in the middle is intermediate. We're going to talk about flexible foundations with limited elastic space under foundations. In other words, gamma infinite with a limited h, which is the distance between the base of the foundation here and the competent layer down here. Second, we're going to talk about rigid foundations with limited elastic space under the foundations. We're going to talk about rigid foundations with an infinite elastic space under the foundation. We've touched on that already. And both of these are going to give different results. We're going to see how different those results are. Let's start with by picking up where we left off in soil mechanics. And where we left off in soil mechanics is the settlement of foundations flexible and rigid. We consider foundations either be perfectly flexible or perfectly rigid. And you'll see in that, you may recall in that table how we did that using that equation in the upper left-hand corner of the slide, right there. And on the left-hand side of that table is given different shapes of foundations, circles, squares, rectangles, and different aspect ratios of rectangle up to the aspect ratio of 10, at which point we give up and say it's a continuous foundation. And we have different settlement. We can do an average settlement, corner settlement, the sag in the middle, all kinds of things. But notice on the right-hand side, we're talking about finite thickening, h. H is that distance from here at the base of the foundation to here at the competent layer. And for different, and instead of trying to to go through all of those different ones, we only consider in this particular table the average deflection under that, and that's all we're going to do with this table. So let's take the right hand side of this table and look at an example. We're going to look at a flexible foundation, gamma is equal to infinity, and a limited elastic space under the foundation, h is less than infinity. Up to now, h has been equal to infinity. Given the problem shown lower right. Lower right says we've got a 20 by 20 foundation. it sits on a 10-foot thick, very soft soil. I mean, if you're talking about a mastic modulus of, in this case, it's 20 KSF, you're looking at some seriously soft soils. And the nu is equal to 0.5. Now, we see this thrown around. Usually this means it's a very soft soil. Yes, it does mean it's a soft soil. But it also means that the it also means that, you know, that's really impossible. At 0.5 would be a true fluid, and they may be close to a true fluid, but they're not a true fluid. But anyway, we're going to say that. And so we substitute, and we take this equation, our governing equation as before, and we substitute in. The only non-straightforward substitution is the omega. The omega comes from the previous slide. It's right here, where we got a square foundation, and H over B is equal to half. 10-foot thick layer, 20-foot wide foundation, 1/2. That's the rest of it is straight up plug and chug. And we get a displacement of 1.17 feet, which, if you stop and think about it, is a lot, considering you've only got 10 feet to displace, or 14.04 inches. And so that is the example of the flexible foundation and the limited elastic space under it. Now we turn to the distribution of stress and the effective rigidity for a semi-infinite soil mass. In the case of a purely flexible foundation, with a uniform load, the maximum soil stress is that uniform load, and that takes place at the interface between the foundation and the soil. And it goes no higher than that. With a rigid foundation, it is entirely different. Elastic theory predicts that the soil stress under the foundation is infinite at the edges and goes to a minimum at the center with a purely. Now, in fact, these two equations for the infinite, the strip load, and for the circular load predict that based upon for a rigid foundation. And you will see that when, for example, the rho, the radius, the distance of a point of interest from the center out to the edge, and r, which is the radius, are the same, this thing blows up. And the same thing where the y, the distance from the center out to the edge, from the middle, hits the edge, B1, the half distance from the middle to the outside, it also blows up. Now, that's elastic theory. In reality, what's going to happen is something along these lines. You'll get a P ultimate, and you'll start getting, the minute you put a load on there with a purely rigid foundation, you will start getting, what you'll start getting is plastic deformation and redistribution of stresses. Now, how bad that is or how good that is depends entirely upon how bad, what your soil is and what your situation is, or how much of it takes place. But that's the theory. And in fact, so therefore, rigidity in a foundation is very important. A very rigid foundation will redistribute its stresses by pushing them to the edges. And that can have consequences. In fact, if you remember from bearing capacity, without getting too fancy about it, two of the points where you had those failure surfaces both started at the corners. So that's consistent with what we're seeing here. Now, if we look at the diagram on the right, then we've got another situation where this shows that distribution I was talking with you about. It redistributes itself, but over here, for different values of gamma, we have a situation where if gamma changes, then the mass distribution, the soul distribution, stress distribution changes. Excuse me. So therefore, if even for change, if we get away from a purely rigid, and we start talking about, flexible but not perfectly flexible. I mean, foundations which are flexible, with somewhat flexible, then the distribution of the soul will change, and it very easily could. It very easily could affect the analysis. And there's one thing I want to make a point of is this. Generally speaking, when we talk about analysis of flexibility, we're going to concentrate on the effect of the soil. Definitely one thing you need to look at in the design of a building is the effect of on the foundation. Plate theory, which is what you normally apply in some fashion to this, is basically beam theory in 2 dimensions. You recall with beam theory you have a stress distribution between the from the compressive side to the tension side of the beam, and how much it depends on the old MC over I formula for your maximum. Well, the only difference between, and I say only, it's kind of a big one, between beams and plates is that plates do that in 2 dimensions. And in some cases they're curved, although most of what we deal with in geotech are flat. And most, and so you've got that to deal with. And though, obviously the foundation needs to be thick enough to prevent failure due to bending in the plate. And plate can get, excuse me, plate theory can be very complicated, although with finite element analysis it gets a little simpler. The next thing we're going to look at is, having laid the groundwork for that, is soil pressures under rigid foundations with a uniform load. Rather than to go through the equations, we're going to present some tabular data. We're going to start, this is a rigid foundation, uniform load. It's either circular or it's a strip load. You will notice the fine print here are the variables. What I did that for was to ensure that you would be able to you would be able to figure out what variables are what. But basically the bottom line is this. First of all, the numbers here are fractions of p. You remember maybe from soil mechanics we talked about influence coefficients. Influence coefficients were the ratio of the uniform pressure at the surface to a pressure in the soil mass. And that's pretty much what we're talking about here. And then we've got 2 different, we've got, we start with the centroid and we go out with little r, or we go out with little y, to a point where we hit big R, the radius of the circle, or B, which is the half width of the foundation. And actually, if that is shown, you can, well, it's kind of weird the way he's got, right, but right here, you see that. 2B1, they actually talk about the half width is B from here to here. Sometimes the notation doesn't quite hold up, which is why I have to keep redefining it with every table. P is uniform. H is the distance, again, consistently from the base of the foundation to the base of the where the component layer hits. So therefore, what we're going to do is we're going to analyze rigid foundations, and we're also going to take into consideration a finite value of h. We're going to get away from the semi-infinite, which all of this is based on. So that's that table. And we can use those either with circular foundations or with strip foundations to determine the stresses under a foundation. And we're talking about at the base of the foundation. We're not really, which is where the maximum stresses take place. Both rigid and flexible, that is true. So for rigid, if we assume a rigid foundation, we can use this to determine the stress distribution under the foundation, and we'll do so shortly. However, I promised you that we would get into the relative flexibility of mat foundations and soils, and we will. The large gamma, what I promised I would give you a formula for it, is right there. And this theory goes back 1930s, 1940s, and it's been elaborated on in various ways ever since. But what we're going to do, and it's based upon, the relative flexibility is based upon two things. First of all, it's obviously the material is just more than two things, actually. First, the relative properties of the soil and the foundation. The soil and the foundation. You have, the foundation has an east of S and east of F, excuse me. Generally speaking, foundations are concrete. There's not very often where we do anything, and usually they're not lightweight concrete. We don't like to get fancy, expensive concretes in foundations. East of S is the moss elasticity of the soil, and nu S again is the nu of the soil, and nu F is the foundation, and L is the half length of the foundation. Now, up to now, I've kind of avoided the issue of a non-symmetric foundation, but it would make sense that the largest deflection of a foundation is actually the largest deflection is going to take place at the on the long ways of the foundation. Although, having said that, it's also possible to go the other way. In other words, to say L is equal to is the half width of the foundation as well. Either one. That would result in a lower value of gamma, which would result in a little bit more rigid foundation, which might get a little bit higher soil stress distribution. So you might want to go both ways. And then T is the thickness of the foundation, which is assumed to be constant. So you can I would suggest that you analyze, if you're analyzing a foundation, to see both ways to see which gamma produces the more conservative result, and it probably will be the one with the lower flexibility, with the lower value, and the lower value obviously would be half of B. So if you were analyzing the flexibility, the deflection of the foundation, you would obviously be more interested in L. But for the soil stresses, probably half of B. All right, then we have another table. This is probably the trickiest table of all for intermediate and rigid foundations. First of all, we have the distance. We have this plot here, and we've got L this way, half widths of L. You could also be half widths of B as well. And we have a situation where gamma can, first this table says gamma is infinite. If gamma is infinite, it's a purely flexible foundation, and once again, the fraction of the P to the maximum in the soil is always unity with a flexible with a flexible, purely flexible foundation. When we start adding rigidity to it, however, the stresses start to redistribute themselves. Now, the way they've done this is they have divided the full foundation into 16. Let me hang on. Let me make sure that's right. Yeah, 16 divisions, which means from the centroid out there are 8 divisions, and each in the centroid of the divisions themselves are in odd 16ths from the center. For example, the first one, this one is 1/16, 3/16, 5/16, 7/16, 9/16, and so on. So they've done that, and what they're saying is that if you can compute the gamma using, probably I would use this formula. The reason for that is that the whole concept, Poisson's ratio, as Voigt points out, is not easy to figure out in soils, and generally speaking, you're better off just kind of using this thing. It makes for a lot easier computation. You can ignore Poisson's ratio. You can go with the elastic modulus of concrete in the soil, the L distance, and the L, and which would be that the half width or the half length, and the thickness, which is T, and you're done. So we're going to just stick with the simplified for gamma. We compute gamma for a soil, which is strictly, and then we say that, is the 0, gamma 0, that's the rigid foundation. Gamma 3, we're starting to get more and more flexible as gamma increases. And for each, and then if it's between those, you would interpolate between them. So, if necessary, a lot of times it's not necessary. So therefore, you start here at L/16th. Notice that for a purely rigid foundation, it's 1, and then actually it goes up as you get closer to as h, which is the distance from here down to the end of the competent layer says, and infinity obviously being a semi-infinite, that 15/16, which is almost the edge of the foundation. Again, with rigid foundations, don't forget, you hit the edge, you hit infinite stresses. But you don't, that's probably not going to affect us. But in any event, we go 15/16, which is close. And as we see, as the h is, as h changes, as h becomes larger, those edge stresses increases. All the stresses keep going up on us. All of them do. And then if we have gammas equal to 3, you'll notice that the maximum stresses start going down. Why? Because the flexibility of the foundation redistributes itself. Redistributes the stresses in the soil. And it keeps going for gamma is equal to 5 and 10. You'll notice that overall the stresses decrease towards the edges as the flexibility increases. They also tend to increase as h gets large, as h gets smaller, you come back. As h gets smaller, the stresses tend to redistribute themselves, and the edge stresses tend to go down, more uniform. And again, I've got the variables defined here. Let's look at an example. Problem shown is lower, the same one as we did the first time. Assuming an E is equal to 720,000 KSF for concrete, assuming that the foundation has a uniform thickness of 0.45 feet, which is 5.4 inches, we're going to find the soil stress under the foundation, considering its flexibility, and soil stress under the foundation is rigid. All right, the aspect ratio of the foundation is unity, it's a square. Likewise, the ratio between either the half width or the half length of the foundation is unity as well. In other words, the half length is 10 feet, thickness is 10 feet, so that's unity. The gamma is done strictly by plugging and chugging here, and we get a gamma 3. Yes, it was planned so we wouldn't have to interpolate on camera, which is a good idea. So anything, we've got the basic, we're down to the basics. Now, since gamma, we're looking at gamma, the rigid case and the sort of flexible case, we're going to start with these variables here. We start with, for the rigid case, since L is equal to H, with H equal to L, and this is a little tricky the way that they've set this thing up, then 1/16 is 0.828, and these are the ratios between the uniform loaded P and the stresses in the soil. So it starts, and the middle actually is slightly under unity, and by the time it gets to the 15/16 for the purely rigid foundation is 1.927. We're going to show what that looks like in just a minute. Then, for gamma is equal to 3, the intermediate foundation, let's put it that way, we have the same thing. We have the same 1, 3, 5, 7, 9, 16ths and all that, but now we've got a different set of coefficients of ratios between the two. So what does that look like? What it looks like is this. I start here with the 16th, and by the way, I usually can keep the 16th decimals in my head because I do fractional design for my consulting part. So once that's done, we have the rigid foundation. These are the coefficients, and these are the coefficients. And of course, flexible foundation is always unity. Rigid foundations, these are the same coefficients, we just transferred them over. Gamma, up to this point, all of this stuff is coming from this table. In fact, I should probably put a box around this because that's where those coefficients came from. And then what I do, since I said P is 4 KSF by the problem statement, in case you don't believe me, once again, 4 KSF, read your problem when you do it. I plot these, and this is what I get. The green line here is what would be if it were a perfectly flexible foundation, 4 KSF across the board, uniform. Now, for both of the other two cases, the case in red is gamma is equal to 3. It's the intermediate case. It kind of moseys across at under 4 until about 0.8. And left of 0.8, it starts shooting up. The perfectly rigid case pretty much does the same, only slightly worse. It's actually, the blue, it actually has a lower stress in the middle, but a higher stress in the end. What that means is two things. First of all, is that it shows that for the purposes of the soil stresses, now obviously, you know, if the structural is a whole different ballgame, but for the purposes of the soil stresses, the difference between a somewhat rigid foundation and a rigid foundation is not as great as you might think it is. That's one thing it shows. And for another, it also shows that for both cases, for the limited height distance, the stresses redistribute them. The stresses tend to redistribute so that they're lower in the. Well, excuse me. I'm sorry. The stresses are actually a little lower in the middle and higher on the outside. In other words, the stresses are lower, and actually the rigidity of the foundation makes for a slightly lower stress in the middle and a higher stress at the end. I think I already said that, but it doesn't hurt to repeat it. So they do redistribute the stress, and that redistribution is significant. Now we're going to shift gears a little bit. We're going to go back before the same stratigraphy as before. Since we already had a rigid, we're going to say instead of having a square, we're going to talk about a circle. 20. Instead, the original problem was a square. Now we're going to do a circle. And we're going to determine the soil stresses for a rigid foundation, and also we're going to do the same thing for under a semi-infinite soil mass. So once again, actually that should be the variable should be little r, and so h over little r, which should be 1, and they should be over under r, and then the formula we have is below for the semi-infinite soil mass. In other words, and then for the table we would use, once again, we would use this column right here. And the results we get, and I tabulate the results on a separate slide, so we'll start there. Y over B1, I need to switch those over to R's, and then Y, the distance from the centroid, the pressure ratios from the chart, that takes it straight off of the chart. These right here go into there, and then the limited layer depth pressure are these from the table, this times 4 to that, and then the semi-infinite half space uses that. These are the ratios, and they come from this formula right down here, and then they result, this times 4 results in that, and then with that we have these results. The semi-infinite half space starts at 2. It starts lower than, but it ends up being higher. The limitation of the elastic space tends to make the stresses more uniform. One of the reasons why we use the semi-infinite is just because in some cases, like this one, it's more conservative. So that pretty much covers this particular topic of the relative rigidity of the foundation to the soil and the limitation of the half space. The last topic we're going to cover in this particular these topics are sort of a grab bag of topics, is really what it is the coefficient of subgrade reaction, how it is useful and how it is not useful. The idea is really pretty simple, and it's illustrated here. If we have a foundation and we apply a load to it, and we keep increasing that load, what we'll get in typical soil stratigraphies, or just for soils, looks pretty much like this, where it starts here and it's elastic up to a point, and then it starts to bend downward. The load hits its maximum, it becomes plastic, and we finally get what we call plunging failure, at which point we stop, and in this case we have an unloading thing where we actually take the load back, and when we're done we look at our result and we have a permanent set. We're going to concentrate on the subgrade coefficient of subgrade reaction on this part of the load right here where it's linear, and we're going to we record as we go down two things for various points. First, we increase the load on it, and then we record the settlement we get out of it. If those are in a linear pattern, or for those of you again who for Excel you've got a series of points, you do a trend line, the slope of that is referred to as the coefficient of subgrade reaction. The units of it are force per unit length, which is actually the same thing as the unit weight, but it means something entirely different. And if, in theory, if we could do that kind of test or do that type of analysis, we could determine the settlement of any, of a shallow foundation without a lot of trouble. And in fact, that's the concept behind the plate load test. Plate load tests, and they're fairly common. Basically, as you see here, you've got a plate, maybe 1 by 1 or maybe bigger or smaller or whatever, and you've got a jack and you've got a reaction system, and a reaction system is a large beam which is affixed to the ground in such a way that it's, for all intents and purposes, rigid relative to what's going on here, and we apply that load progressively. We're going to see the same concept and sometimes, very similar looking results when we get to stag load testing with piles. But in any event, this is what we do. And all we're testing here is not a pile soil system, but just a soil. And we get that kind of result, which looks like that. And we're able to determine what the subgrade reaction is. Now, obviously, like I said, if the problem is, and if you look at this photo, it becomes immediately apparent. Civil engineering is generally not about small foundations like that. You'll see them occasionally, but most of the time are bigger than that. And if we were going to do a full-size test, then we would have a situation where we would have a big foundation, we would have a big load system, and potentially, we would have a a situation where we would, the load where we just couldn't do it, where the load, to construct a loading cell like that would be just too large and too expensive. What could we do? Well, if you take the small one, we could try to extrapolate those results. We could say, well, we could do one or two things. We could say either that, well, the coefficient of subgrade reaction is the result. We can see this line right here, and we can get the coefficient of subgrade reaction and apply it to your big foundation, live happily ever after. Or we could, and that's not right for reasons I'm going to show you in just a minute, or we could try to extrapolate those results. And that has perils too. Let me explain first from elastic theory why that doesn't work. And then we'll see from there why we'll see why the extrapolation is dangerous as well. Okay, let's start with the whole problem with the coefficient. If I were to take the equation we've been using to determine the settlement, the equation with omega in front of it, and I were to combine it with the equation of subgrade reaction that I had, then and combine it, I would get this. The coefficient of subgrade reaction in terms of the elastic coefficients is equal to that. Now, we know that modulus of elasticity and or shear modulus is a product, is a soil property. Let's assume that they're uniform, which is dangerous in and of itself. Poisson's ratio, the same thing. Omega is a function of the geometry, at least with B. The problem is, you look at this equation, and the problem really is staring you in the face. As B increases for a given soil, as B increases, K sub S goes down. They're inversely proportional to each other. The K sub S is not a true soil property. It is the result. It is the product of, it is a function of both the soil properties and the geometry. And it means that as the foundation gets larger, the K sub S becomes smaller. And as a result, you have, and that's also, and the other problem is that if you remember, we had those influence bulbs. You remember back a few slides back, we talked about the stresses under a soil and those stresses are a function, in part, of the size of the foundation. The larger a foundation, the deeper in the soil it goes. The deeper in the soil goes, the more possibility you have of getting different conditions or even hitting a competent layer. So, which probably would work in your favor if you did. So, in any event, K sub S is not a true soil property. And in fact, if you'll notice in this, old DM7, and I think the new one does the same thing, you have to extrapolate those results. And extrapolation is always a dangerous thing to do in engineering. But it is within the limitations of the test. It is a way we can use to determine that. And if if the stratigraphy will work for it, we can use the plate load test to actually, we can expand on that to estimate settlement. One thing I'll make mention of right here is that one of the major applications of plate load testing, or any kind of surface rigidity testing or flexibility testing, is pavements. All pavements is found very long, large foundations, and the load is whatever rolls on top of it. And there are other ways there are other tests that we use in pavement technology to determine the settlement. And that's important because if you've got a settlement issue in pavement, you're going to have a very rough road to travel over. And that happens more often than we care to admit in road construction. And there are many factors. But I just wanted to note the fact that pavement technology is one of the things that really drives this type of shallow foundation testing. Therefore, what we can say is that the size of a foundation is what drives its settlement. And as I said, if B is increasing, the K decreases. If K decreases, then the settlement increases for a given load. And this chart here is a nice illustration. The square root of F basically is the square root of the foundation's area, which is kind of a pseudo length depending upon whether the foundation is rectangular, circular, or whatever, or square, or whatever. This particular diagram came into play about 30 plus years ago when a pair of researchers were looking at the problem of settlement of shallow foundations or dynamic loads, and in the comments that they got back, once you publish an ASCE paper, you get comments back. A friend of mine who actually is from the Ukraine, I believe he's from the Ukraine, but he's definitely from that part of the world, came in and pointed out, using this diagram, the fact that size effects were a major problem. And it just shows that sometimes it's easy to overlook important aspects of foundations in the design, even at the advanced level of research. Other problems include the fact that soils are nonlinear. They strain soften. The higher the strain you have, the higher the stress you have, the lower the shear modulus is around that area. That's something that is being explored more than it was, say, 30 years ago. And of course, mechanical properties change with depth. The coefficient of subgravity is extensively used. There are other ways of doing it, of determining potential settlements and pavements, but it's one of them, and it's one that you should be aware of its existence and of its limitations. So that concludes my presentations on shallow foundations. Thanks for watching, and God bless.